This is your presenter, Asloob Mudassar, and I am presenting slide number 7 of the course on atomic and molecular physics. In the today's lecture, I shall be covering Rydberg atoms, their production process, their detection process, and some physical properties will be covered. Rydberg atoms, I shall abbreviate them as RAs, Rydberg atoms. Atoms excited to very high quantum number n are called Rydberg atoms and have extraordinary properties. Rydberg atoms are gigantic with diameters approaching 10 to the power minus 2 millimeter, which is 10 to the power 5 or 100,000 fold increase over the diameter of atoms when they are in the ground state. So compared to the ground state, the Rydberg atoms have usually large diameters of the order of 10 to the power 5 times their diameter they usually have in their ground states. Rydberg atoms have extremely long lifetimes, up to 1 second, whereas the lifetime of an ordinary atom in the excited state is of the order of 10 to the power minus 8 seconds. So here you can imagine the long lifetime of the Rydberg atoms. And this is the long lifetime of the radiative decays, where the photon will decay. So this is the radiative lifetimes of such levels. Rydberg atoms have energy, that is the photons emitted by the Rydberg atoms satisfy equation number 7.1, that is En minus En prime is equal to h nu, where n and n prime are two quantum states in the Rydberg atoms. So for the Rydberg atoms, this quantity, that is the difference of energy between two consecutive levels, is very small for large n values. So for large n values, the spacing between the levels becomes smaller and smaller, and so this energy difference becomes smaller and smaller as we reach higher n values. So since Rydberg atoms are in the Rydberg atoms, we go for large values of n. That is, we excite the atoms to a very large values of n. So if the atoms decay between two consecutive such levels, then of course the difference of energy between these two levels will be very small, as stated in equation number 7.1. The probability of spontaneous emission represented by A21 between the n and n prime levels according to the Einstein is proportional to the nu to the power 3, where nu is the frequency of the photon emitted when the transition is made between the level n and n prime. And the formula is given as shown in equation number 7.2. So A21 is equal to 8 pi h nu to the power 3 divided by c to the power 3, and this term is multiplied on the right hand side by the value by B12, where A21 is the probability of spontaneous emission, because we are decaying from the level 2 to the level 1. So this is the probability of the spontaneous emission, and B12, where we are going from level number 1 to the level number 2, is the probability of spontaneous absorption. So the relation between the probability of spontaneous emission is related with the probability of the spontaneous absorption through a term which is given as 8 pi h nu cube over c cube. As nu is small between two consecutive levels, as I have stated in equation number 7.1, that is when the transition between two consecutive levels is made, where delta n is equal to 1, then h nu is a very small quantity. So nu is also a small quantity there. So as nu is small, A21 is also small, and implies that the lifetime of the state in a Rydberg atom Rydberg atoms is large. So you see that from here we can directly we can indirectly follow that since A21 is a small quantity, so it means that the lifetime of the spontaneously emitted state is very large for the Rydberg atoms. Rydberg atoms can be strongly polarized with relatively weak electric fields. So this is one of the properties of the Rydberg atoms. There are some properties that we are just mentioning them, but we are not going to prove them because their domain goes out of the atomic physics domain. So because they are the problems that we normally discuss in classical physics, so here we are not going to discuss those properties, but we are just mentioning some of the properties. So the Rydberg atoms can be strongly polarized with very weak electric fields. So the stress is on the weak electric field. In the Rydberg atoms, an electron excited to large n values, such an electron sees an atomic core to be consisting of the nucleus along with all the inner electrons like the hydrogen nucleus. So since a single electron is excited to a very high level, then of course the electron at a very high distance away from the nucleus will see the nucleus and the inner core of the electrons around them as if the shielding electrons are shielding also the nucleus of the charge. So effectively the nucleus charge will appear to be +1 because the electron is at a very large distance having a charge -e. So under that condition, the electron will see as if the nucleus is that of a hydrogen-like atoms. So all atoms, for example, for the hydrogen nucleus, if we are talking about the hydrogen atom, then of course where we assume, according to the Bohr theory, that the orbits are circular. So if the electron is away from that one, then of course the electron will be away from the hydrogen nucleus. But you see that if we are talking about the hydrogen-like atoms, where the nucleus is not there are many electrons around the nucleus in their closed in shells, and the electron which is further away from the nucleus center will see as if the nuclear charge the nucleus has a charge as +e, because the electron has a charge -e, because the inner electrons will then be shielding the nuclear charge. And in such an atom the electron will see as if in such an atom we can regard the Rydberg atoms to be consisting of hydrogen like atoms. And you know that in the hydrogen like atoms we assume that the nucleus is appearing to be nucleus of the hydrogen atom, and around which a single electron revolves. If the electron in a Rydberg atom does not approach the core too closely, it behaves like a hydrogen atom. So you see that this is an important condition. You know that in the Sommerfeld model, we assume the elliptical orbits are assumed there, where an electron can also come closer to the nucleus. But here we are assuming that the electron should come closer to the nucleus, but not as much as possible in the normal Rydberg in the normal Sommerfeld orbits. So we say that if an electron in a Rydberg atom does not approach the core too closely, it behaves like a hydrogen atom, or it behaves as a hydrogen-like atoms. Rydberg atoms may thus be regarded as highly excited hydrogen atoms or highly excited hydrogen-like atoms. In interstellar space, Rydberg atoms with quantum numbers up to 732 have been observed with astronomical methods. So you can imagine the quantum number as 732, and these Rydberg atoms have been found in the interstellar space. So using astronomical methods, they have observed these Rydberg atoms to be occupying this state of a principal quantum number, that is 732. Rydberg atoms with n is equal to 700 to 1000 have been achieved in laboratories. In routine studies, researchers study Rydberg atoms in the range from n is equal to 50 to n is equal to 100. So in the routine study, you don't go to a very high value of a principal quantum numbers because that requires a very high level of efforts in order to achieve Rydberg atoms to be occupying a state in the range from 700 to 1000 value. But you see that normally the Rydberg atoms could be studied in the range from n is equal to 50 to n is equal to 100, which is relatively much easier, and many properties of the Rydberg atoms can also be studied very easily. Due to large values of n, the Rydberg atoms have special properties. Sizes could be in the range of several micrometers. So you see that this is very important. In the range of several micrometers, that is the atom, that is the atomic size becomes much greater. Extremely sensitive to the external electromagnetic fields. So this is another property, that the atom is very big, the electrons is locating at a much larger distance from the nucleus, and so the atoms becomes very extremely sensitive to the external electromagnetic fields, that is electric fields independently. You can also call it a magnetic field independently, or both. If both fields are present, then of course it is also very sensitive to the magnitude of both electric and magnetic fields. So possesses long lifetimes. This is what we have briefly established through the spontaneous decay constant, which is smaller, and so the lifetime, as we have established in the previous slide, that they have normally long lifetimes. And these lifetimes are the lifetimes of the radiative transitions, where when the decay will takes place, the atoms will emit a photon, according to equation number 7.1. So electron being much away from the nucleus present the atom as a classical body, because the energy levels when the electron is much away from the nucleus, then for example in the range of 700 to 1000, if you are exciting the Rydberg atom in this stage, then of course the energy levels becomes so close to each other that we can say that they are very they are that in a very they are in a continuum region, and we can study such a Rydberg atom to be consisting of a classical body. And these may be interacted with strong long range dipole and van der Waals forces. So you see that long range dipole interaction is possible with such a Rydberg atoms, and also the van der Waals forces can also have a long range with such a Rydberg atoms. So you see that these are just the findings of the researchers that I am just explaining them. But you know that if you want to explain them in the real sense, we need some mathematical derivations of these problems. But you see that this is beyond the scope of the present course. Applications include that Rydberg atoms act as qubits due to their strong interactions, and can be used to create quantum gates used in quantum computing. Rydberg atoms can be used to detect and to measure electromagnetic fields with precision. Rydberg atoms can act as single photon sources, because if you want to observe a single photon, then of course the Rydberg atoms are the best choice, where you can have a single photon emission from these Rydberg constants when there is a transition between two selective levels. So you see that Rydberg atoms also find their applications in the field of quantum qubits, in the case in the field of quantum computing, because they can be used to generate quantum gates, and independent Rydberg atoms can also act as qubits. Rydberg atoms are produced by exciting an atomic beam with the laser beams simultaneously. So you see that many laser beams could be used, to excite the Rydberg atoms to the higher states. Some lasers are used to are used for intermediate excitation, and the other lasers could be used for precision excitations, where you can selectively move the Rydberg atoms to their next excited states. To detect the highly excited atoms, an electric field is applied between the plates of a condenser through which the atomic beam passes. And it is necessary that the control of electric field within the condenser should be very precise, so that if you ionize an atom, for example, in the state of n is equal to 50, then if you want to ionize the atom in the state n is equal to 51, then of course it means that a very precise value of the electric field through the condenser is applied. So the condenser, which is used for the ionization, to achieve the ionization of the Rydberg atoms, should have a very precise control over the electric field between the two plates. The electric fields, which is of the order of hundreds of volt per meter, ionizes the atoms, and the ions are detected, which are converted into the electrical signals. So let me show you the description of the experimental setup. You can see that an atomic beam is coming out from an oven and is being illuminated in the present figure by three different lasers. So three different lasers are used to illuminate or to excite the atomic beam. And you see that at the point of illumination, or at the point where the beam is being excited, across that we have placed condenser plates, and we can very selectively provide specific values of the electric fields, and we can ionize a specific state in the atomic beam, a specific state of excitation in the atomic beam. And with that one, when the excitation is ionized, when atoms, Rydberg atoms in such excited states are ionized, then you see that they can be attracted through these potentials, these electrons, because one of them is negatively charged plate, the other plate is positively charged. So the ions move towards the negative charged plate, and there is a space between the two plates, and the electrons can move towards the electron multiplier, where the ions are detected. So the detection of these ions will indicate that under the specific application of the electric field, that you have ionized a Rydberg state. So you can infer the information about a particular state of the Rydberg atom, that which Rydberg state, that the atom that what was the state of the Rydberg atom, and how much electric field was applied in order to ionize such Rydberg atoms. So you can selectively get information about the excitation states of the Rydberg atoms by ionizing them precisely with the precise values of the electric fields applied within the condenser plates. Several laser beams of different wavelengths are focused on the atomic beam. The sum of quantum energies of the laser beams matches with the desired excitation level in the atomic beam, creating desired quantum state n. The Rydberg atoms are ionized in the electric field of a condenser, providing variable voltage potential, because the condenser is such that it can provide a variable voltage potential with precision. The ions are thus detected. In the previous diagram, the atomic beam is produced from the lithium atoms. So lithium beam is excited by three laser beams. The first two lasers excite the beam to an intermediate excited state. For example, say with the principal quantum number 30 and orbital quantum number equal to 0. So you can excite using two lasers. The lithium atom can be excited to this state, n is equal to 30, with L is equal to 0, while the third one is a continuously variable laser beam, and this will within a small energy range. So you see that this provides a continuous variable energy in a small continuous range. Thus, a particular Rydberg state can be chosen by tuning the frequency of the third beam. So you see that in the today's world, very precise laser systems are available, which can provide a very long tuning range, or a long continuous tuning range, and where we can selectively ionize the, where we can selectively excite the Rydberg states, and even also can selectively ionize the Rydberg atoms. Emitted light is in the range of infrared or microwaves. Isolated Rydberg atoms were first discovered in 1965 in interstellar space. Due to low density of the Rydberg atoms, collisions are extremely small. So you see that it is a prerequisite for the detection of the Rydberg atoms that their collisions with other atoms should be very rare, so that you can find these Rydberg atoms to be independent or isolated, and you can detect them. Due to the availability of narrow band tunable lasers, Rydberg atoms can be investigated in laboratories. And you see that the value of the quantum states, which I have given earlier, that is in the range from 700 to 1000 principal quantum states can be achieved in the laboratory, and this is because of the narrow band precision laser beams. So due to the availability of narrow band tunable lasers, Rydberg atoms can be investigated in laboratories. Energy levels, lifetimes, spatial extension of wave functions, and the effect of electric and magnetic fields on the Rydberg atoms are now possible to study. So you see that many parameters and many properties of the Rydberg atoms can be studied very easily and very precisely, because these atoms are now can be possibly generated within a laboratory setup. So here you see that I am going to give you the excitation of the beam that we have created over here. For example, in this setup, this was the beam that was generated from this is actually a lithium beam, and the lithium beam, you see that we studied the lithium beam for the Rydberg atoms. The lithium beam was finally ionized, so that we can detect information about this quantum state of the atom of the Rydberg atoms in the atomic beam of the lithium, in the lithium atomic beam. And once these beams are generated, you see that we can ionize them. For example, this is the plot where the signal is fed to the ion detector. So detecting the intensity of the ions, you can see that we have given the principal quantum numbers was varied for such Rydberg atoms in the range from n is equal to 20 to n is equal to 39. So this is the level n is equal to 20. You can see the strength of the signal which was detected by the ion detector. And then we have moved to the next state, n is equal to 29, then to the state n is equal to 30. And you can also notice their magnitudes. The magnitudes are also decreasing. And then you see that you have moved to the higher quantum states, n is equal to 31, 32, 33, 34, then 35. You can also notice their magnitudes. And of course, so on the other quantities, because of course the magnitudes could vary, because there is a probability that some transitions have higher cross sections in comparison with the other quantities. So some lines corresponding to some principal quantum numbers have lower values as compared with the others, because the cross sectional areas of such transitions could be variable and is not fixed. And you see that along the vertical side we have plotted the energy in centimeter inverse, and these are the negative quantities corresponding to each principal quantum state of n, and these depict you the value of the binding energies of electrons of the Rydberg electrons in those states. The figure shows the Rydberg states from n is equal to 28 to n is equal to 39 for the lithium atom, that is for the lithium beam as used in the previous setup. These states can be measured using the apparatus shown on page number 3. So you see that this is the apparatus that was used to measure the voltage, to measure the signal from the detector, ion detector. So these states can be measured using the apparatus shown on page number 3. When a Rydberg state falls by n is equal to 1, that is, there is a decay of higher state to the first to immediate lower states where the quantum state vary by n is equal to 1. Light in the far infrared or microwave is emitted. Any state can be selected and excited to the desired level to investigate its physical properties. So you see that now it is physically possible that we can excite any particular quantum states, and there we can also study their physical properties. The Rydberg atoms are hydrogenic, that is, can be categorized as hydrogen-like atoms. That is, the outermost electron in higher quantum states see the nucleus surrounded by inner cores of electrons, which will shield the nuclear charge, and the nucleus charge will appears to be plus E, that is like that of the hydrogen atom. And because the outermost electron in higher quantum states has an electronic charge equal to minus E, so you can regard them as hydrogen or hydrogen-like atoms. So such atoms are also regarded as hydrogenic. So here we are presenting some properties that the researchers have investigated. So these properties are being outlined, especially for the Rydberg constants. For example, En, the binding energies of the electrons, goes as 1 over n square, or n to the power minus 2. These are the binding energies, and of course, very weak binding energies, because as you go with the higher quantum states, the n increases, and so 1 over n square becomes very small. So the binding energies of such states becomes very small, or you can say extremely small binding energies when the electrons are in the higher quantum states. Delta E, that is the change in energy between the closely lying levels when the transition takes place from one level to another closely lying level. The emitted energy delta E is proportional to n to the power minus 3. So it changes as cubic power of one over principal quantum number 1 over principal quantum number raised to the cubic power. So this is valid for the closely lying levels where n is small, and delta E energy will be proportional to the 1 over n cube. So if you are working with Rydberg atoms in very higher quantum states, then of course the delta E will be very small quantity. The average value of the radius for the Rydberg atoms is proportional to the value of n square. And this value of the average value of R is usually greater than 1 micrometer, because we excite the Rydberg atoms to such a level that the diameter becomes 1 micrometer, greater than 1 micrometer, where it becomes very easier to study the physical properties of the Rydberg atoms. So this is mu, which is the dipole moment of the Rydberg atom. It is proportional to the value of n square. So larger mu means stronger coupling. So since n is a proportional, mu is a proportional to the value of n square. So if you are working for the Rydberg atoms with high quantum states, then of course mu will be a very large quantity. So it means that larger mu means stronger coupling between between the outside systems or between the outside systems. For example, you can interact them through dipole-dipole interactions or through van der Waals forces. Alpha, which is the polarizability, varies as n to the power 7. Again, you see that this polarizability is very, very high for these quantum, for these Rydberg constants, for these Rydberg atoms. And you see that when the polarizability is very high, it means that the Rydberg atoms are very, very sensitive to the electric fields. So this is very important property. And the lifetime tau of the radiate, this is actually the radiative lifetime where the photon is emitted, and the radiative lifetime of such states is proportional to n to the power 3 when the orbital quantum number is small. But when the orbital quantum number is also very high, then of course the lifetime goes as n to the power 5. And you can see that usually we work in the range of 100 microsecond. When the lifetime is in this range, then of course the different properties of the Rydberg atoms can be studied and analyzed. Now the dipole-dipole interaction. These dipole-dipole interactions goes as is proportional to the n to the power 4. Again, you see that this dipole-dipole interaction would be very large, would be very significant because it goes with the power 4 of the principal quantum number. So strong interactions over long ranges. So since a dipole-dipole interaction is very strong for the Rydberg atoms, so it provides you a possibility that you can interact with such a Rydberg atoms from remote, that is from over long ranges. The van der Waals forces the van der Waals forces goes as n to the power 11. So the interaction due to van der Waals are also much greater and can be interacted over a very long ranges. Then the geometric cross section is also very significant, goes as n to the power 4. So this geometric cross section, the greater value of the geometric cross section means that we can easily ionize such Rydberg constants. So you see that these were some properties, these were the ideas, and why we have studied the Rydberg constant with the hydrogen atoms in the chapter of hydrogen atoms. The reason was that these Rydberg atoms can be treated as hydrogenic atoms, that is hydrogen like atoms, and the usual the formulas of the formulas that we have discussed under the atomic models of the Bohr and the Sommerfeld can be applicable for the calculation of energies and other parameters. And of course we can also apply classical formulas for the study of these properties of the Rydberg atoms. So this is the end of slide number 7 of the course on atomic and molecular physics.